Hi everyone, and welcome to another seminar of Physics Latam. Today we are very happy to have José Edelstein. He's a professor of theoretical physics at the University of Santiago de Compostela, and he will talk about higher curvature corrections to general relativity, theory, and applications. Please remember to raise your hand if you have any question, and I will leave you with José. Please go ahead.
Thank you, Daniel. Well, thank you everyone for joining to this talk. So, just before starting, let me explain you that this has been the subject of my research in the last I don't know, maybe 15 or years, or maybe even a bit more. So I wanted to, and I hope you will enjoy it and you will learn from it. I wanted to summarize somehow the subject, at least my view on the subject. This is a broad subject. There is people working on it that probably will disagree with my approach, but basically what will do is to summarize my own experience in the subject. And I will try to be very conceptual in the sense that I will give lots of technical details, but whenever I have to choose, I will try to choose that you learn something instead of entering into a very technical stuff that you miss the point. So to start, so of course you can interrupt me whenever you have questions. I'm sorry, I have the chat in a side of so I am looking at the chat also. If anyone, if there is something in the chat, I will see it. So the idea that is probably very familiar, but just to put everyone in the same pace, let me just start. So the idea is we have general relativity. You know, it's an amazing theory. It's very successful in terms of its predictions and the um, tests of the predictions. However, we have good reasons, and I will go very briefly over them, but roughly the fact that general relativity is a classical field theory that doesn't allow quantization. And we can discuss later in the questions. I mean, we have several reasons why it's inconsistent to have a universe in which every other interaction is governed by quantum mechanics, while gravity doesn't. If you want, the most obvious reason is that there is Einstein's equations have curvature on one side and matter in the other side. So in the right-hand side, let's say where matter is, you have quantum field theory, and there is an equal sign. So it's better than the left-hand side also is quantum mechanical. If not, that's completely inconsistent. So the rough idea in which I would say everybody would agree in all different approaches to this problem is that GR is well behaved at long distances. This is actually the cases in which we do experiments. And at some point, at some distance, there should start to be deviations from GR. The deviations could be as dramatic as you may think, but an important point that we have learned from the language of effective field theories is that typically the deviations arise as some sort of non-local terms that are higher derivative terms. Basically, the idea is the following. If you see my pointer, there should be a scale, a length scale. I am calling it L star, which I can also use lambda star, which would be the energy scale, at which some deviations appear. And then, since the action must have units of a number, and we have the volume in the integration of the Lagrangian, we need this length scale to be accompanied by a gradient to have something that is dimensionless. So let me just to be more concrete. For instance, this is the Einstein-Hilbert action. This is the cosmological term. And then if you want to include some scale lambda star, in this case the energy scale, since this is dimension full, you need to have derivatives in the numerator to keep the engineering dimension of the operator, the 4, such that the action is a number. So in this particular case, you may think of a correction that has lambda star in the denominator, But in that case, you will have only one derivative, and Lorentz invariance will not allow you to make to build a Lorentz scalar term in the action with a single power of lambda star. Then you need to go to the second power of lambda star. In that case, you have two further derivatives. The Riemann tensor has two derivatives of the metric. So then basically what this means is that the term should be quadratic in the curvature. So this is a particular combination of so there are three quadratic terms in the curvature, the Riemann square, the Ricci square, and the scalar of curvature. And this is a particular combination that I will talk about in a second. But in particular, you have three terms, and you can have three couplings in front of them, okay? The point is that whenever you add these terms in the action, the Euler-Lagrange equations will become higher order. And higher order Euler-Lagrange equations are typically problematic. I mean, it doesn't mean that they are not allowed, but typically, if you try to quantize a theory with higher order, well, not quantize, typically higher order equations have more degrees of freedom, describe more degrees of freedom. And if you analyze the propagators of the particles that are correspond to these theories, well, typically you need to have you have propagators that are like 1 over p4 plus something, and that when you want to write this in terms of 1 over p squared propagators, the typical propagators of a massive particle, you will have to subtract propagators to get the 1 over p4. And this subtraction means that there is a propagator, there is a propagating field with the wrong sign in front of it. Or if you want, there is a degree of freedom with the kinetic energy with a minus sign. And that's typically problematic. I mean, it's very hard to make compatible this kind of behavior. Anyway, I will come back to that later in the lecture. Because well, there were many interesting new results very recently about that I think make us think that, well, things may be a little bit subtler than you may think. Now, you may ask, is there any combination or combinations of higher curvature terms that lead to second order Euler-Lagrange equations? And the answer has been given by David Lovelock in 1971. So it's a very old, well, especially I guess that the audience is as young as Daniel. So probably I was alive when Lovelock did this demonstration, but you were not. So it's a theorem. And as you know, a theorem is something that has no possibility to get rid of. So there is a theorem that tells you that to a quadratic order, for instance, there is a single combination that is the one you're looking at now in the slide. If you have a 1 minus 4, 1, this particular combination leads to second order equations. However, and I will show you in a second how you can see this very easily, even if you see this term, I mean, you will never realize that this term in 4 dimensions is a total derivative. It's completely impossible to realize that, well, to my knowledge, just from scratch. However, there is a different language in which this becomes manifest. So the price to pay to have second order Euler-Lagrange equations is going up in the dimensionality, because in 4 dimensions this term is a boundary term, so it doesn't contribute to the equations of motion. From 5 dimensions on, this term uh, influence the dynamics of the system. And actually, for every single order, so this is quadratic, but then you may ask, is there a cubic, is there a quartic, is there a quintic? Yeah, to any order you have a single combination that leads to second order Euler-Lagrange equations. And this combination is non-trivial in the sense that it's not either zero or a boundary term, only when the dimensionality of spacetime is greater or equal to k plus 1. So then we have if we want to study these deviations from GR, we have a problem, no? Because, well, we either do this, we use Lovelock theories. Lovelock theories are extremely well behaved, and I will talk I will talk the next 15 minutes about it. Or 20, or maybe more, maybe 30 minutes. So they are amazing theories, very well posed, has many nice features. in particular, coming from the fact of these second order Euler-Lagrange equations. However, they are higher dimensional. There is nothing you can do to prevent them from being higher dimensionals. So, okay, well, anyway, I guess that you have heard, everyone, probably all the audience have heard talks about ADS-CFT that I will talk about later. In ADS-CFT, you have the gravity theory is higher, has at least one more dimension than the field theory. So then, okay, if you have a four-dimensional quantum field theory, the ADS dual will be five-dimensional. In five dimensions, you may write the term you have in front of your eyes. So it may be interesting. The Lovelock theory can be interesting for holographic applications, and it is, and I will tell you later how it is. Um, and maybe even to try to explore what happens if you go to even higher dimensions, just out of a theoretically minded person. I want to see what happens there. Or there is another option, and I will basically use the second part of the, I understand that the seminar is divided in two. So the second part I will devote to the second strategy that would be trying to stay in four dimensions, to try to do phenomenology more cleanly, so to say. But then the price to pay is that you will not have such a nice theory as Lovelock theory, and I will tell you later about the kind of theories you may try to construct to do that. So let me go to Lovelock theory, and I hope you well, maybe some of you have seen this, but if you haven't, I will go very quickly over this way of writing the Lagrangian in terms of differential forms. It's not that well, it's fancy, yes, it's cool, but also it makes many things more clear. So if you haven't ever seen differential forms, never mind. I mean, it's simply a way of a calculus that is has some rules. So the rules in particular is that you have what forms. The forms are either differentials like dx mu or wedge products of these differentials. These wedge products are antisymmetric. They have some obey some rules. And the nice thing is that there are two basic rules that will make life very easy. First, if you want to integrate a differential form, this will only be non-zero if the differential form is the same order as the dimension of space-time. So any thing you want to write here has to have, if we are in d dimensions, has to be a d form. It has to have d terms of this sort. Then this is the Riemann curvature. Notice that even if it has two indices, really, if you decompose it as a form, it's the Riemann tensor, the coefficients of this form are the Riemann tensor coefficients. So then each of these guys is a Riemann tensor, and it has two Lorentz terms, two Lorentz indices in the tangent bundle of the space-time, let's say. So then you have, I don't know, k of these guys, and then these other guys that are filling the expression are the Firbeins. The Firbeins are something like the square root of the metric. So you can build the metric with two Firbeins. And then these are one forms, these are two forms. So if you have k of these forms here, this is a 2k form. And since you need a d form, there have to be d minus 2k Firbeins. So how many of these terms I can write? Well, as many as combinatory analysis allows you to do. So then actually there is a sum between 0, you can put k equals 0, so no curvature. If you put no curvature, I guess that you realize that this is a cosmological term. K equals 1, one curvature is the Einstein-Hilbert term. K equal 2 will be the previous one, which is called Langsos-Gauss-Bonnet term, etc. And the sum will finish at the integer part of d minus number 2. Basically, it's very easy to realize that, because if not, you will have too many forms here. This will be, the form will be, if you have k greater than this, you will have a form here that is bigger than the space. And you cannot integrate a differential of volume in a surface. This will give you 0. So I just mentioned this by, I just mentioned this, that For instance, the term k equals 0 is a cosmological term, and actually in this language, c are the coefficients. If I put c0 equal to 1 over L squared, where L is a unit of length, this will correspond to a cosmological constant with this expression here, which is like the canonical way to relate the cosmological constant with the ADS or DS radius of spacetime. Then k equals 1 is the Einstein-Hilbert term. And just to give you an idea, if anyone wants to play an exercise, you can check that if you put C1 equals 1, this is exactly putting 16 pi d minus 3 factorial g Newton equals 1. Is the canonical normalization to get rid of the Newton constant. And this k equals 2 term is a Langsos-Gauss-Bonnet term that I showed you earlier. So this is the quadratic example that is there are, of course, I don't know, hundreds of papers analyzing this particular Langsos-Gauss-Bonnet term. Why? Because it's the simplest one beyond GR. So it's something that we as physicists typically do. Remember, for later, we will use these theories. So remember that lambda is the dimensionless coefficient of the quadratic term. You can go to the cubic order. In cubic order, believe me that if you do, it's a very nice exercise to show that this expression, when you put k equals 3, if you are trying to learn exterior differential calculus, it's a very nice exercise, and it's not easy to show that if you put k equals 3 here, you get a particular combination of the 8 possible terms, cubic terms. No, you have Riemann, 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 well, Riemann, Ricci, Ricci. So you have all possible combinations, and there is a single term, no, with the 1, 3, 16, etc. I'm not interested in the particular expression, but I can give you references later. And this happens for every single k. So remember for the future that mu will be the cubic coupling, because I will work a little bit with the cubic theory, including the quadratic and cubic theory, because, well, the quadratic is too simple to show some things. The cubic has all the richness that we will need. So one of the nice things of writing the Lagrangian in this exterior differential calculus language is that the equations of motions are amazingly trivial in this language. So if you vary the action with respect to the Firmine, well, the Firmine enters the action. I hope you remember. I don't want to be coming back and forth all the time, but the Firmines enter in this particular way, which is algebraic. So the differential equation, there is no derivative on the Firmine. So the differential equation is simply reducing one. It's simply like the derivative of a power. So it's very, very easy. This is actually the differential equation. Is written here. Of course, the sum over the repeated indices is assumed, and there is a single free index, which is the index of the field that we varied with respect to it. And then I wrote this in a different way, in which these curly f's are this particular combination between the Riemann two form and the product of two Firmines. And notice that there are some numbers here. These are some numbers. And it's obvious that if you let me, for the last time, come back to the action. So this is the action. So this sum over a sum including many different terms of different orders with some coefficients in front of them. If I vary with respect to one of these fields, I will get a similar combination, except for the fact that I have, for instance, I have here d minus 2k Firmines. So then when I vary, I have d minus 2k options to vary. They are all the same. So then this factor will go away. That's the reason of this factor. This will go away in the equations of motion. And then the resulting equation I can reshuffle in this particular way, in which, of course, these lambdas will be functions of the coefficients of the action. Okay, but the nice thing of writing in this way the equations is that it's obvious that the solutions of these equations, well, there are many solutions, but there are the most symmetric solutions, which would be the vacua of the theory, will be simply that these guys vanish. If any of these guys vanishes, This means that we have a constantly, remember that when the Riemann is constant, this is a maximally symmetric spacetime. If lambda is zero, is Minkowski spacetime. If lambda is positive, is de Sitter, and lambda is negative, is anti-de Sitter. So then we have k possible vacua, because any of these curly f's can vanish. So this in principle will give you k, capital K, remember d minus 1 over 2 integer part, this is the number k, possible vacua. And but you may have less, because they can be the same. I mean, it can happen that if you choose particular values of this constant, some of the vector can be the same. And that, actually, this is quite easy to write in these particular terms. If I replace in the equations of motion r equal to lambda EE, then what I get, the solution of that equation, plugging into the equations of motion, the vacuum, so the constant curvature, sorry, ansatz, so to say, what you get is that a given polynomial of this of the constant curvature has to be zero, and the polynomial is exactly the polynomial that the formal polynomial that you will write using exactly the coefficients of the action. This is, please try to follow the argument. Believe me that the computations are quite easy, so you can then later try to do them. And I will show the example of the quadratic theory that I think you can follow very quickly, just at face value. So this will be, this polynomial upsilon of lambda will be very important for us, but it will contain a lot of features of the theory. In particular, this polynomial can be, will have k roots. I mean, there's the fundamental theorem of algebra. Of course, some roots can be complex, for instance. So if a root is complex, of course, there is no meaning, for us at least, to a space-time with a Riemann curvature that is complex. No? So it's in principle, one may discuss that, but I will be very conservative. To me, I only want real space-times. So that's why also I wrote here up to k vacua, because you may have some possible vacua that are complex, so they are not vacua of the theory. Whenever you have a polynomial, you can write something called the discriminant. The discriminant is the subtraction of all possible roots of the polynomial, squared to get rid of the sign. And then if the discriminant is zero, this means that at least two of these lambdas agree. So let me show you the quadratic case, which is very easy. Actually, it's just the quadratic formula we learned in high school. So if you put k equals 2, well, remember upsilon lambda is a quadratic formula, so then you can find the roots. Of course, the roots follow the typical formula minus b plus minus square root of b squared minus 4ac, etc. In this particular case, this is expression. And then you can see that the discriminant, actually in high school, we called this expression in below the square root the discriminant. That's where the name comes from. Delta is equal to 0 whenever lambda is 1/4. I will call this lambda 1/4 lambda CS. In a second, I will explain why. Then you can see that whenever lambda is lower than 1/4, this is a real value. Then you have two possible values for the lambda. And this means that the quadratic theory has two vacua. Well, both have negative signs, so they are two ADS vacua. Okay? So this theory has second order Euler-Lagrange equations, that's good. And this has two ADS vacua, that's weird. I mean, we have to make sense of that, but okay, there is no problem. A theory can have many vacua, and this theory has two ADS vacua. These guys, Bolver and Desser, showed 40 years ago that the vacua with the plus sign is unstable. And I will come back to this point later, because this will be very interesting. The interpretation of this result. Well, let me continue. When lambda is equal to lambda CS, this will be 0. There is a single vacuum, but this single vacuum is very special because it's not a single vacuum like one of these two ADS vacua. This is a vacuum where the symmetry has been enhanced, because in a theory that with would be two possible vacua, the two vacua coincided. There is a symmetry enhancement. It may be not obvious to you at this moment, but believe me that if you, this actually, Ali Chamseddine realized this in 1989, and this is the origin of the CS. CS means Chern-Simons. Chern-Simons are very particular theories. The most well-known Chern-Simons theories are three-dimensional, but they arise in any odd-dimensional space-time. And this is a Chern-Simons, whenever you, if you tune lambda to 1/4, this is a Chern-Simons theory in 5 dimensions. And this is very special. It has a lot of features. The symmetry is enhanced. There are, the solutions are divided in different sectors, in the sense that there are some solutions that are degenerate, in the sense that if you go to a solution and you perturb it, the perturbation, the equations of motion for the perturbations are 0 equals 0. So it's very strange. There are no quadratic perturbations for these solutions. And the theory is topological in a sense that I will not discuss today, but I can give you references to check that. So this mathematically is a very interesting case, this, and it belongs to a whole family because remember we are analyzing the quadratic case. For all possible cases, there is this particular possibility. There is a Chern-Simons theory for any odd-dimensional gravity with corrections. And then finally, whenever lambda is greater than 1/4, so then this is a negative number, there is no real square root, and this means that there is no ADS, neither ADS, no DS, no flat, so no vacuum, okay, no real vacuum. So I will call that an excluded theory because there is no, I don't know, a theory with no vacuum makes no sense to me, at least. Now, we I told you that Bolver and Desser realized that the plus sign branch there. So there are two ADS vacua. You can think of putting the theory in a given vacuum and perturbing it and finding solutions around that vacuum, as we do normally in any theory. But then you can find that the plus sign vacuum is ill-behaved in many different ways. And in particular, the negative sign, the good one, has positive derivative of the upsilon polynomial. Is this a coincidence? No, it is not. You can show this is not what Bolwer and Desser did, but this is like the more generic way of understanding why there is a problem with the plus vacuum, is that when you take the theory in the vacuum and you perturb it, you find the perturbations, that spin 2 perturbations are gravitons. So then the gravitons will have a linearized field equation in which there will be a coefficient playing the role of the Newton constant of that graviton. And the Newton constant is basically the inverse of upsilon prime. So then we clearly understand why the plus vacuum is ill-behaved, because the plus vacuum would have gravitons that are ghosts, no gravitons that have a negative sign in front of the kinetic energy, and that's, as I mentioned, is problematic. So I will, whenever I generalize these two Lovelock theories to any order, to any order, there will be, I will only care, the only stable senseful vacuum will be vacua, will be those with a positive upsilon prime. Okay. Now let me make for the first time a short deviation to the CFT side of this result. And this is very nice because, Lovelock theory, you can write Lovelock theory in 1,000 dimensions if you want, in 1,000,000 dimensions, in whatever dimensions you want. Formally, there is no obstacle to writing the theory. So then you can formally use the ADS-CFT formula to compute things of the one-dimensionless CFT that would live in the boundary of the ADS spacetime of the particular well-behaved ADS vacuum of the theory. And amazingly, things work pretty well, even if you are in whatever dimensions you are. So this is something that is very weird, because if ADS-CFT was obtained in the framework of string theory has 10 dimensions. Maybe it can have 11 dimensions in some particular regime, but it doesn't have 1000 dimensions. So it's very weird. This, and I will show you some very nice results that work in whatever dimensions you want to think of. So I'm not going to, I hope you all have seen something about ADS-CFT. If not, the only thing I will say without any plot or formula or anything is that ADS-CFT is a given framework in which the gravitational physics in an ADS d-dimensional space-time has the same information as a particular CFT living in one dimension less, and in particular, we always think that this CFT theory lives in the boundary of the. So this is was formulated by Juan Maldacena almost 30 years ago. It has some even early ideas by Brown and Henault in three dimensions, and it was, as I guess you know, probably the most celebrated results in the last quarter of a century. And certainly there has been more than 20,000 papers working on this subject, improving and improving and improving it. So basically, what is improvable? The improvable is building up the dictionary, because whenever you claim that a gravity theory in d dimensions is equal to a CFT theory or a quantum field theory in d minus one dimensions, well, you have to provide a dictionary, because any quantity you can compute in the QFT, you will ask the person who asserts that this is a duality, so there is an equal sign between both theories. You will tell the person, okay, how do I compute, for instance, a two-point correlator in the CFT? So this is a scarce energy tensor in the CFT. If I compute the two-point correlator in the CFT, this is totally fixed by conformal symmetry. And Osborne and Petco showed that just the the index structure of this quantity is given by just conformal symmetry, force you to have this particular index structure. There is no second index structure that satisfies the symmetry. The dependence on the distance between these 2 points is also fully given by conformal invariance, because conformal invariance in particular contains scale invariance. Scale invariance means that if this is an operator with dimension energy dimensions 2, and this is 2, 2 plus 2 is 4, so you all the dimensions, all the dimension full part has to be given by the space-time separation. There can be no coupling or anything containing dimension full coefficients. So then all the dimension full dependence of this correlator is given here, and then the only free thing you have is a number. This number is called the central charge, CT, and then you can, these kind of correlators, there is one of the, let me call it the golden rule of ADS-CFT, is the rule that tells you how to compute correlators in the boundary. Was one of the first things that were studied. This was established in two papers very soon after Maldacena's work by Edward Witten and Gabser, Klebanov, and Polyakov. And I will not explain this here because the subject of my lecture is different. But believe me, there is a way to compute this. So if you compute this correlator using the ACFT, the ADS-CFT dictionary for Lovelock theory, you get this very nice result. Well, I think it's nice because it only depends on upsilon of lambda. This is in principle non-trivial, that the result only depends on the polynomial that I showed you before. And in particular, for a given ADS vacuum of the theory, so you will put here your favorite ADS vacuum. Since it's ADS, this will be positive, though, so this will be a real number. And then you can clearly see that whenever upsilon prime is positive, the central charge is positive, and if they are negative, both are negative. But if this number is negative, the CFT is non-unitary. So here we find the first nice result. It's very general, and it's the fact that we have realized that in any dimensions in Lovelock theory, demanding to have a vacuum with
Buenos días.
gravity. Yeah, I will come to the question now.
Just
having gravitons with a positive sign in the kinetic term or positive sign in the propagator is the same as having a unitary CFT in the boundary, and this is generic. Yes. Mm. There was a question or there wasn't? Okay, use your hand to or the chat if there is a question because I listened someone speaking, but probably was a microphone.
if there is a question
Dan-
in the chat, I can read it for you. It's okay.
No, no, I can also read it. I have in front of me the chat,
Ah,
so don't
okay, okay.
worry. But I heard some noise and I thought someone was willing to say something. Okay, so let me go to black holes in these theories because it's you. I hope you will find this very nice because the black holes are amazingly simple. And we are talking about, I am telling you that if you want to compute the black hole solution of a 1000 dimensional theory with 500 terms in the action that look very complicated, it's amazing that the black holes are simple. And this is so. Let's take the ansatz for the metric, like the canonical ansatz for a black hole, in which you have the let me call it blackening function. It's colloquially known in this way, this f of r, that in the Schwarzschild solution would be 1 minus 2 m over 4 over r, and then the transverse part will be a transverse space section that will be either a sphere, a flat section, or it's maximally symmetric in d minus 2 dimensions. So I will keep this sigma here. If sigma x plus 1, this will be a sphere. If sigma is 0, it will be a flat um, plane, a hyperplane. And if sigma is minus 1, it will be a hyperbolic space. So if I plug these ansatz into the equations of motion, regardless of how difficult they are, and they are difficult, there is a combination of the equations of motion that is very simple. And is I will not show you the details, but in the exterior differential calculus is quite simple to get to this equation, in which you combine all the equations and you can find, surprisingly, that the upsilon polynomial, I hope you recognize by this moment the upsilon polynomial, but not with lambda, with g, where g is sigma minus f of r divided by r squared, so g of r is related to f of r. This particular combination has a ordinary differential equation of first order, which is trivial to integrate. So this is surprising. This was first obtained by Wheeler. Not This is J. Wheeler, but not John Wheeler, but James Wheeler. But okay, it's not the most famous Wheeler that probably you're aware of. Okay, so we can integrate this. So the solution is given here. It's the upsilon polynomial of G is given by k kappa over r d minus 1. And you can now use, for instance, the Hamiltonian formalism or the definition of the conserved charge in the boundary to realize that kappa is connected to the mass. As you may expect, because there is a single parameter for the solution. It's a black hole, so what can it be if it's not the mass? Of course, it can be. You may say it can be the electric charge, but okay, you can of course play the same game with the Reisner-Nordstrom black hole, but this is not. I haven't included, and I will not include any other field than the metric. So this is as probably expected, as I said, the mass and some numerical coefficients. It doesn't matter. So then notice that here you have, well, there are two things I want to notice. First, you have k branches, no, because this is a polynomial that, remember the quadratic case. In the quadratic case, you had two possible branches with two vacua, and there will be one black hole per each vacua approaching in the boundary the particular ADS vacua you're choosing. And in the generic case, you will have k, this k, capital K, vacua with so k branches of black holes. So I'm writing here again the previous expression for you not not needing remember it. It's upsilon equals this combination here. So notice the following. There is well, first, remember that if capital K is greater than 4, you will have a polynomial that is order 5 or more. And there is a theorem that is under the name of Abel and Galois that tells you that there is no possible way to solve a polynomial, to find an analytic solution for a polynomial order greater than 4. So this is one bad news. The bad news is, okay, you will not be able to find an explicit solution unless k is at most 4. Okay, that's bad. But anyway, I mean, the theory is sufficiently complicated that we wouldn't expect to find a solution, maybe a numerical solution, but not much more than that. Here we are in a better situation because we have an analytic solution. So we have actually k analytic solutions, but they are implicit. So this is simply an implicit function. That's not very dramatic. I mean, we know from, I don't know, for the first year of the career that there are functions that are implicit, so no problem, but they are analytic. This is a good thing. So how we can analyze this solution? So imagine that epsilon of g. So this is epsilon of g. So imagine for a moment that epsilon of g, a particular, so it's a polynomial. If you plot it, it will be a curve, a curve. This curve, imagine for a moment that has some part of the curve that is this one here, okay? So notice the following, and this is very interesting because if you get the idea, you will realize that this is very simple. Whenever r is infinity, then this is 0. So then this means that let's focus on a given branch. So on a given branch, when r is equal to infinity, or r tends to infinity, I will have epsilon equals 0. So then I will have one root of the polynomial. For instance, this root here. And then whenever I go from infinity to the interior of the spacetime, so r is now very large but not infinity. This means that this quotient is very small as a number. So I am equating the same polynomial with a number that is small. So it's equating the polynomial is always a blue line. The small number will be then the first dashed line you find on top of the horizontal line. And of course, this equation, the solution of the equation is intersection of those two curves. So then I know that for this particular value R1, that is very large, but not infinity, very large, G of R is the solution of this particular, gives you the particular point I am plotting in the blue curve, because it has to be the intersection of between this number and this curve. Then I can take R2 a little bit lower than R1, R3, R4, etc. And I can, in principle, in my brain, build the solution by imagining all the intersections between the the upgoing horizontal lines with the blue curve epsilon of g. In particular, whenever in the particular case sigma equals 0, remember, sorry, that g is sigma minus f over r squared. For a moment, imagine sigma is 0. So then the horizon of the black hole will be placed where? Well, at the point where f vanishes. If f vanishes, g vanishes for the sigma equals 0 case. So this means g vanishing is this particular point here, g equals 0. So this means that here is when this point will be the intersection between the epsilon polynomial and the horizontal line of height r plus. Okay, so notice that there is something unbelievable in this, which is that even at least conceptually, I can, of course, the particular numerical value of g of r, okay, is something I can find from numerics or from any other analysis you may think of, but conceptually, g of r is simply the function that will give you from infinity to r plus all the intersections of this particular curve here. So this is very useful if you want to find whether there are singularities in the middle, whether there are phase transitions, whether there are lots of things that are typically very difficult to find, and in this way of analyzing things, you can find those results very easier. Yeah, in an easy way. I'm realizing I'm going too slowly, but if you want to know more about it, let me see. Okay, I will explain a little bit more here. But then, if you want, there is There is in particular, black holes in Lovelock theory. There is a paper I wrote with my former student, Sean Camaño, titled Lovelock Black Holes. No, a Lovelock Black Hole Bestiary. This is the title of the paper. I can give you later the reference. And there is a whole detailed explanation of all possible black holes, all possible branches, all possible scenarios that you may think of. I will go to a very simple scenario here because I want to show you a very beautiful theoretical result. So now let me come back to the sigma different than zero case. Recall that G is this thing here. So whenever the horizon is the point where f goes to zero, so G plus will be, to me, G at R plus will be sigma over R plus square. Here you have it, sigma over R plus square. So whenever I have epsilon of G plus equal to K kappa over R plus to a D minus 1, but if I replace R plus in terms of G plus, I see that the intersection to see whether a black hole has a horizon, I have to find an intersection between this epsilon G plus curve and this particular curve here. And it can be that there are no intersections. For instance, imagine that this is a cubic case. So this is a particular possibility for the cubic black hole, for the cubic theory, sorry. So in the cubic theory, the curve, this curve here, with this blue and red, for reasons I will explain in a second, this is simply a cubic curve. So for the particular values of lambda and mu, remember the coefficients of the cubic theory, this would be the curve. So then notice that the expression here in the right hand side, in order for this to be positive, to be able to take the square root, if sigma is plus 1, G plus has to be positive. If sigma is minus 1, G plus has to be negative. So then this this function, G to the D minus 1 over 2, because there is the square root, is roughly a growing function, a monotonically increasing function that will go to the right for sigma equals plus 1 and to the left for sigma equals minus 1. So this, let's consider there are three ADS vacua here, this point, and this point. This one has negative derivative, so this will be a problematic vacuum. This will have ghost gravitons propagating around this. So let me neglect this vacuum. I mean, of course, I can tell you things about this vacuum, but at zero order, let me neglect it. So there are two well-behaved vacua here, these two here. And then notice that, for instance, if the mass, remember that kappa is roughly the mass in some units. If the mass is very large, 2 in some units, no matter, so then the curve, this curve will be grow very quickly. So for instance, sigma equals minus 1 is a hyperbolic black hole, a black hole that has a hyperbolic horizon. You can see that there is this branch of the solutions has a black hole with this mass. The G of R will be given by all the values from the infinity to the horizon. Remember that in the previous slide I showed you that G of R will give you all the values in the curve from the horizontal axis to the point where the curve cuts the curve of the black hole horizon, which will be this one here. So if I ask you, is there a black hole of mass 2 for a hyperbolic black hole for this branch? Yes. Is there a black hole of mass 2 for this blue branch? No, because the blue branch never intersects this curve here. Okay, that's something we didn't know before. But if we go to a mass, which is this very low mass, with 10 to the minus 3, then you can see, well, the curve is this one here. That is very, well, here you cannot see it departing from the horizontal axis, but of course it departs. So, I mean, it starts here. So then you can see that the mass equals 10 to the minus 3 intersects both the red branch and the blue branch. This means something very nice, that in these theories you may have, for a given mass of the black hole, you may have the degeneracy, two possible solutions for the theory. So then this immediately raises the point whether there are, if you turn on, black holes have temperature. If you put the black hole in a thermal bath, you may have more than one solution competing to be the lower state. So then the whole subject of phase transitions, canonical and microcanonical, grand canonical ensembles appears. And this is quite interesting. I will not tell you because this is a long story, but you can, for instance, for this particular black hole, you can ask what will be the preferred state for the system. Of course, notice that there is a subtlety here. This black hole, the one that in the blue curve, has a different asymptotics to this one, because remember that this is a cosmological constant. So you may think, and this could have been a question that you didn't ask, that okay, maybe these two black holes have the same mass, but they have very different asymptotics, so they will not belong to the same ensemble. But that's not so obvious because you may have, and actually I there are some papers I wrote. You can read those papers if you want, in which you can see that there is a a mechanism for phase transition called the Thermalon mechanism, in which what can happen whenever you have two solutions that are competing, and there is one that is preferred, but you put the system in the other solution with a different asymptotics. So then you say, okay, the non-preferred branch will be accepted by the system because I chose the asymptotics that is the asymptotics of that branch. But that what may happen, the thermalon is an Euclidean solution that basically what it shows is that a bubble can be created with the right branch in the interior and the wrong branch in the exterior. Well, the wrong in the sense that the non-preferred in the exterior, the preferred in the interior, they both have the same asymptotics, so this bubble can appear with the same asymptotics, but then the bubble is unstable, and it may even collapse or grow. And if it grows, it can take over the whole space-time in a finite proper time, in ADS in particular. So because in ADS it takes a proper time to get to the boundary. So then the system can, even if you put the system with these asymptotics, it can it can have a phase transition to this branch um, through the Thermalon mechanism. This is quite an interesting subject. It brings a lot of questions to that may be interesting. For instance, of course, if you choose in a different way the coefficients of the polynomial, in a cubic polynomial, you may have roots in the right-hand side of this plot. In the right-hand side, this will be ds, the Sitter vacuum. So then you may ask whether it's possible to have a transition from ADS to DS. No, a system that is originally was ADS, but through the Thermalon goes to DS. And the answer is yes, this may happen. So this is something that is maybe very interesting because, as you know, ADS-50 works very well in ADS spacetimes, but we apparently live in something that is asymptotically DS spacetime. So this is an interesting subject that has not been explored that much, in my opinion. Notice that in the spherical case, also you can see that if I take the mass very low, now imagine that this curve here, I will make it very flat, then I may have spherical black holes, no, spherical spacetimes that do not have horizons. Because in order to have a horizon, I need this curve to intersect this other curve. But this is a cubic one, this is quadratic. So in 5 dimensions, sorry, in 5 dimensions this is cubic and this is quadratic. So it may eventually go always below the other curve. That would mean that for that particular mass there are no black hole solutions. That would mean something very strange, that for these theories there is a lower mass for the black holes. There cannot be black holes, there cannot be small black holes. The black holes start from a given mass. All these things I am mentioning, people studied and they are very interesting, and I will urge you to study. Let me tell you in the last, well, maybe more than 5 minutes, but I will try to go fast, to a particular application that I think is really surprising. So this is something that was developed originally by Hoffman and Maldacena in a paper that the title of the paper is Conformal Collider Physics. And the reason is that they used a language of collider physics to build a particular computation of a something in a CFT. So the idea in collider, as you see, this looks like a collider process in which there was a collision here, and then the particles go to the detectors. But here the idea is different, but it's the same plot. What I will do is I will construct an operator. So this operator is complicated, as you see, but it's in a sense not that difficult. You take the stress energy tensor, component 0i, you multiply, contract with a unit vector in a given space-time dimension. So this n will point, it's a unit vector pointing to infinity in space. Then you do this contraction. You evaluate this at time t and radius rn. So you evaluate this along this n direction, not in any point, but along this direction. And then you integrate from minus infinity to plus infinity, as if you were collecting all the energy flowing in that direction from minus infinity to plus infinity. So that's like that. That's the reason of this plot. It's like if I had calorimeters in every point in space, and I am collecting all the transfers of energy momentum tensor in that particular direction from the beginning of time to the end of time. So this is a definition. So I mean, this is a quantity you can compute. And then the interest would be, and you will see why very soon in the coming slide, I can compute the expectation value of this operator in a state, and I will choose, the discussion is longer, but I will go to the particular point that is interesting for me, which is I will take this operator, which is again the stress energy tensor, with the contracted with some polarization. This epsilon ij is some symmetric to index tensor that I contract with the stress energy tensor to find some, well, depending on epsilon ij, we'll have different components of the stress energy tensor. With this operator, I act on the vacuum, so I create a state. With this, I create a bra. So this is the expectation value of the operator E, divided by the norm of the state I created. So this, the nice thing of this quantity is that, I don't know if you have seen something about CFTs, but in a conformal field theory, both the 2-point correlator, so this one in the denominator, and the 3-point correlator, this is a 3-point correlator because here I have T, here I have T, and here I have T. So this is 3 T's. All the rest is irrelevant. There are 3 operators that are T. Both the 2-point and the 3-point correlators in a CFT are fully determined by conformal symmetry, except for a couple of numbers. So in particular, believe me, and this is absolutely non-trivial, that just out of the symmetries of the CFT, the only possibility for this expression is there are 3 possible terms. The isometric term, 1, which is equal in all directions. This particular term, which is quadratic in the unit vector n, which is epsilon, remember, was a polarization of t, n was the unit vector. So this is like contracting the polarization of t with n and multiplying by its complex conjugate as a vector. So this is like the n squared, but of course you have to contract all the indices, divided by the norm of the polarization. And forget about this number. It's simply a number, a normalization number, because when I integrate in all the sphere that surrounds the point where I inserted operator, I want to have, I am integrating in all the, at infinity, let's say on a spatial sphere, I want to have the total energy. So the total energy is epsilon is zero. This is the total angle, like 4 pi, for instance, in the case of the 2-sphere, but in more dimensions, this will be whatever I need. So this will integrate to 1 when I integrate in the at infinity. And this number is just put here in such a way that the integration of this term at infinity cancels with this 1 over d minus 2. And the same thing with this one. This is the other possible expression I can have, which is contracting the polarization with 2 n's and then taking the mod square to have a real number. And again, this number is just a normalization issue. So all the structure in this expression is fully fixed by CFT arguments. And there are only two numbers that are free, T2 and T4. So this is something that comes from CFT. T2 and T4 can be computed for, of course, remember what this quantity is. T2 and T4 must depend on the coefficients of the Weil anomaly. I will come back to that in the case of 4 dimensions in a second. So now well, of course, I can be worried whether there are some minus signs here in some points, and T2 can be positive or negative, but we don't know what T2 is. So I can be worried about the positivity of this vacuum expectation value. And then I can analyze, this is a very canonical procedure. I'm not going to explain the details, but you can analyze the so-called tensor, vector, and scalar channels. That would mean those the all possible orthonormality properties between epsilon and n. So this is it's not that difficult to do. And then you have positivity of the energy will give you three algebraic conditions on T2 and T4. So this is a linear equation in T24. So this inequality will tell you that you are in one side of this particular straight line in the T2-T4 plane. You are in a given side of this particular straight line in the T2-T4 plane, and you're in a given side of the straight line of this different straight line. So I plotted for you the three straight lines, and believe me that the region that is allowed by these three conditions is the interior of the triangle. So we got to an amazing, well, surprising, maybe surprising result. Certainly when this was originally obtained, it was surprising that not all values of T2, T2 and T4 are compatible with positivity of the energy. They have to be inside the triangle to be compatible with positivity of the energy. In particular, T2 and T4 equals 0 is, of course, this point here. But then I can turn on T2 and T4 and see where it takes me. So I know that if I turn on, if I include an operator in a CFT that, I don't know, makes T4 lower, this is the minimum value I can reach. If I go further, this will not be a positive energy CFT. So let me, I will consider particularly do expectation, vacuum expectations for channels. Sorry, I see that there is a question. I'm reading the question. No. So in the well, I mean, yes. So you can insert this operator O. No, remember that epsilon was related to O. So you can choose the O with a given polarization compared to the direction to which you are pointing. And then doing that, you are choosing each of the three channels. But of course, you want this result to be valid for the whole sphere. So no matter the polarization you choose, whenever you choose all directions, you will be choosing all the channels. But you can separate the three different channels because they will correspond. Remember this picture of the calorimeters? They will correspond to different calorimeters at infinity. So you want all of them to have positive energy. That's why you have to satisfy the three algebraic conditions and not only one or two or a subset. You need to satisfy the three of them. So let me focus in the case of vanishing T4, in particular because, well, this is superconformal field theories, so conformal field theories with supersymmetry have T4 equals 0. You can prove that. And Lovelock theories have, using the holographic dictionary, you can compute T4, and it also vanishes. This is, please notice that it doesn't mean that Lovelock theories are part of a supersymmetric theory, necessarily. Okay, they coincide, they both make T4 vanishing, but to prove that Lovelock theories are the bosonic part of a supersymmetric theory is something nobody has done, and it's not obvious at all, and it's probably false. But let me focus in this particular case, T4 equals 0. So in that case, well, if you go back to a triangle, T4 equals 0 means you are in the horizontal axis. So then there is a minimum value of T2 negative, a maximum value of T2 positive that you can simply play. You can find it very easily from here, and it's these two expressions here. So let me show you an amazing result. And oof, I am going so slowly. let me focus in the particular case of four-dimensional superconformal field theories. It's well known, and I am not going to describe it because it's a long computation, but I can point the references. That so in a conformal field theory, this is the trace of the strategic tensor should be zero. But there is a conformal anomaly in superconformal field theories that tell you that this is not zero in quantum when you include quantum mechanical the quantum mechanics in it. This is not zero, and it's proportional to the Euler invariant and some two invariants that are connected to the Riemann curvature of the four-dimensional space-time. In this slide, I am not using yet ADS-CFT. This is four-dimensional physics. So there are only two numbers that are typically called central charges, both of them, C and A, that are the coefficients of the Weil anomaly or the trace anomaly equation. In particular, in four dimensions, if you compute T2, I told you T2 has to be a function of the Weil anomaly coefficients. So actually, if you compute that, T2 is 6 times 1 minus A over Z. So then in four dimensions, you can plug this T2 here, and it tells you that A over C is in a finite range, lies between 1/2 and 3/2. This was surprising when this was originally found by Hoffman and Maldacena. If you put GR is T2 equals 0. So T2 equals 0 is A equals C. So this is the case 1, which is in the middle of this window, of this range, okay? That's the GR scenario. But of course, you may think of CFTs in which A is different than Z. So it's immediate that if you want to do holography for conformal field theories where A is different than C, you have to turn on the quadratic term, for instance, because that's the only way that, at least at the moment, we found to move from the point A equals Z. Now, imagine that you compute T2 in using the holographic dictionary. T2 is this nice expression. Again, for me, it's nice. Why? Because it only depends on upsilon, again. So T2 being in this range via the ADS CFT dictionary tells you that upsilon of lambda, remember we found before that the first derivative of upsilon in the vacuum should be positive. Now we have another condition. Now this weird combination has to be in this range here. So is this connected? So for the moment, I only used ADS-CFT to convert T2 in upsilon. But is there a computation I can do in the gravity side to show that there is a gravity feature that also needs this requirement? And the answer is yes. I will go very fast through it because I'm running out of time. And actually, Daniel, please interrupt me whenever you want because it's a disaster. I'm seeing that I'm handling very badly the time. So you can do some very beautiful computation, which is take the black hole, the Lovelock black hole that I showed you before, go to the boundary and throw to the interior of the. Remember, we are in ADS. ADS has a boundary. You can throw to the interior a perturbation, and it can be a spin 2 perturbation, spin 1 perturbation, or spin 0 perturbation. The three cases are different. You can analyze three cases, and you can see that the perturbations they have a differential equation they follow with a potential, a sort of gravitational potential for the perturbations. The gravitational potential is actually, you can check that it's the value is exactly the speed of that particle at that place of the potential. You normalize the speed to be 1 at infinity. Remember, we are talking about gravitons, so you have to go to the speed of light, 1. So they are 1 in the boundary. And you can see at the first correction to the boundary, that's why I put this not equal sign, but soft equal sign, because it's the first correction to the 1, is something that, again, can be positive or negative. If this is positive, this means that the graviton will enter space-time and will have a local velocity that is above the speed of light. That's still not necessarily a problem, but the problem is that we know that at the horizon it has to go to zero. These c squares. So then this is a soft function that goes up, and then it has to go down to go to zero at the horizon. So then you can imagine you do a Gedanken experiment. I tuned the energy of my graviton for it to go up the slope, stay above the hill as much as you want, and come back to the boundary. So this will be a perturbation going to the interior and coming back to the boundary. All the time, this perturbation had a speed greater than the speed of light. So then, of course, the average is greater than the speed of light. And that means that the observer in the boundary, which is a CFT observer without gravity, will experience a superluminal propagation. This is forbidden. This forbids. This is very problematic for of course, for relativity. So this means that we necessarily need to impose that these three corrections have to be negative, all of them. I mean, lower or equal zero, such that all the c squares are lower or equal one. If you do that and you plot this in the cubic theory and the lambda mu plane, you get these very weird but very nice, I think, nice curves in which the causal region, so the region without superluminal propagation, is the white region here. Of course, the point 0, 0, where lambda is 0 and mu equals 0, which is GR, of course, is causal. GR we know and we hope it's causal. And when you turn on lambda mu, well, you can turn on lambda mu, but you're going to turn on whatever lambda mu you want. So this is the first restriction we find. You cannot do whatever you want. Now, if you turn on lambda, then there is imagine mu is 0. You turn on lambda, there is a maximum value of lambda, after which causality will be violated. So this excluded region, remember, is the region where there is no vacuum. Remember, maybe it's the most memorious of you will remember the 1/4. 1/4 is 0.25, which is exactly this point here. So this was where in the Gauss-Bonnet theory the excluded region started. This is the maximal value of lambda allowed by causality. And a nice issue is that whenever you turn on mu, imagine I turn on mu to this value, I can go further in lambda without violating causality. And this was a very interesting result, and I am finishing, I think, with this first part, because in the some 20 years ago, people used ADS-CFT to analyze quark-gluon plasma physics, and in a very beautiful paper, these people realized that if you want to compute the viscosity of the plasma, this is the shear viscosity of the plasma, there is something called the Cubo formula that tells you that this is the zero frequency limit of a correlator. The correlator can be computed with ADS-CFT very, very easily. It ends up being the absorbing cross-section of a black hole in the zero frequency limit. This is proportional to the area. The area is proportional to the entropy via the Bekenstein-Hawking law. So then you can find that eta over S is 1/4 pi in natural units. And this was a surprising result because first it was coincident, so to say, with the experimental data. You know, in 2000, there was the relativistic heavy ion collider in Long Island that for the first time produced quark-gluon plasma, and when the analysis of the data was compatible with a very low shear viscosity. Nobody was able to understand why, and these people found out that if the theory is strongly coupled, you may use ADS-CFT and you will get a very low value, which is 1/4 pi. Then these people conjectured that this is a lower value in nature, but then you can compute the case, you can compute for Lovelock theory. This guy Xu did it a few years ago, and you can see that eta over S is 1/4 pi. The quadratic term is the only one contributed. You can have 500 terms in 1,000 dimensions, but the only term that contributes will be the quadratic one. So this presumed lower bound will go down when lambda is positive, and there is a maximum value of lambda given by causality, as I showed in the earlier plot. So people typically assumed that since there is only the quadratic term here, the cubic term was irrelevant for this discussion. But we found out in this paper that this is not the case, because even, let me come back to this, even if it only lambda is relevant for that formula, whenever I turn on the cubic case, I can go further in lambda, and I can take down the bound on et over s. So then this bound is not true, and this bound is violated by higher curvature terms. And in Lovelock theory, there is an issue whether I can take that value, that lower bound, to zero. And if you want to know the answer, you have to read this paper. So I will stop here for the first half. Okay, good. So let me, so I will not have time to tell you everything I wanted, but let me try to continue at the pace that I think is the right one to make things understandable. And then with in the last part, I will probably go very fast, showing you some possible applications that are nice, interesting, and I hope you find them in this way. So let me come back, even if I was talking a lot about Lovelock theory, and I want to ask a different question that is very important for physics, and in particular for from the theory point of view, is that, okay, for the moment the only restriction I put to myself is to use to construct terms that are Lorentz invariant, because I was contracting all the Lorentz indices, so they were scalars, so okay, great. They were local, great. And now, can I do that? I mean, is it true that or any local Lorentz invariant operator I write leads to a consistent answer? And the answer to this question is no. And let me show you the people who realized this in the context of QFT was these people here. And they showed in a beautiful paper in which actually they analyzed a lot of systems. I am showing you here the particular case of the Maxwell action, but they do this for many systems except gravity, because gravity has a subtlety that I will show you later how to solve. So they asked themselves, imagine you have the Maxwell term, which is this one here, and with the same argumentation I made at the beginning of my lecture, imagine that you say, okay, well, the theory is probably not complete. There should be higher derivative corrections. They should have a nice tensorial form. So they should have contractions of this sort. So the next term will have two more derivatives. So if this is zeroth order, this has to have the scale to the fourth power, because you have the two derivatives plus the gauge field has also one dimension. So that's why here the two derivatives lead to a fourth order, because you have two derivatives and two a's. Okay. Then you can contract f with f or f with the dual of f. These are two different terms. There will be two numbers, C1 and C2. So this is just putting the terms as I put before the Lovelock terms. Then can C1 and C2 be whatever I want? Well, we already saw in the case of Lovelock that they cannot be whatever you want. There are some restrictions coming from causality. This is the last part of what I explained. However, those restrictions were very mild, in the sense that if you remember the eagle-shaped white region I showed you, and I don't want to come back, the eagle-shaped was non-compact in the left. So you could have arbitrary lower negative lambda and mu, and that was not restricted by causality. And it's very weird to imagine a theory in which you correct GR not perturbatively, but with a non-perturbative coefficient. So these people analyzed this in the case of U1, and they computed the S matrix, so the scattering matrix of photons, for instance, in this particular theory. And they showed that if C1 and C2 are negative, then everything is a disaster. Analyticity of the S matrix is violated, unitarity of the S matrix is violated, and superluminal modes appear. So C1 and C2 can be zero or positive, but they cannot be negative. And it's a very interesting result, because they show this without knowing. So the idea is that these terms come from integrating out degrees of freedom in a theory that you don't know or you may not know. So they show that even if I don't know the full theory, I can already know that C1 and C2 cannot be whatever you want. And then the following thing you may think of is that, okay, but wait, if I have such a familiar theory as Maxwell theory coupled to fermions, I can, in the path integral, integrate out the fermions if they are massive, and then I will get an effective theory for the photon that will have these two terms. So what is the value of C1 and C2 in those cases? And you can check that if you do the computation for this particular case of fermions coupled to, or electrons coupled to Maxwell field, and you integrate out the electrons, C1 and C2 will be positive. So a theory we know that is a well-posed theory satisfies this criterion, as of course it couldn't be different than that. But okay, you can check that. So what about gravity? So in the case of gravity, my idea would be to also check whether I will add two terms to the action, this particular contraction of the Riemann squared and Riemann cube. Notice that I am not doing Lovelock, but I will tell you in a second why it's roughly irrelevant that it's not Lovelock what I'm doing here, but in a second. So what I will show in case you fall asleep is the following. I will show that C1 and C2 have to be 0, roughly. And if I don't put an equal sign here, it's because I have this scale lambda star, and lambda star can be, I have never told you, sorry, lambda star, what's the value of lambda star. So if I push lambda star towards the Planck mass, then I cannot any longer constrain the C1 and C2. That's why I put this symbol here. In other words, this plot summarizes what I'm doing. Oh, sorry. So you have the energy, you have the Planck mass, quantum gravity should arise here, strongly coupled gravity is in this regime. So I will assume that there is a lambda star sufficiently far apart from the Planck mass, such that gravity remains weakly coupled here. So gravity is still describable by a smoothly deformed curved spacetime. And this is the case I will explore. You can tell me, okay, maybe there are no theories like that. Maybe there is the family of theories with these conditions is the empty set. But we know it's not the case because perturbative string theory is within this set. Why? Because lambda star in perturbative string theory is roughly given by alpha prime, the length of the string. And the length of the string is a very small quantity, so the string is very small, but is farther apart from the Planck length. So the inverse of both of them are exactly in this situation here. So this result was obtained in already a few years ago with Xian Camaño, my former student, Juan Maldacena, and Sasha Shiboyedov, his former student. Now they are, well, Sasha is a well-accomplished scientist at CERN after a few years. So what I will do is the following, and I will be very schematic because the details, of course, will take me the whole lecture. What I will do something called the iconal limit of the scattering of two gravitons. So I will take two gravitons. Imagine I will do them collide head-on, one towards the other, but with an impact parameter. Okay, they go in opposite directions, but they are separated with an impact parameter. In principle, I will work in any dimensionality, so the impact parameter is a vector in the transverse plane. With the direction of motion of both gravitons, and time, I will create B and U, the light coordinates. So, and I will work in the particular regime in which the center of mass energy, which is given by the Mandelstam parameter S, will be very large, and the transferred momentum between gravitons, which is given by the T Mandelstam parameter, which will be very small compared to S. Okay, so this is the regime in which I will do the computation for reasons that will be clear. Well, for a reason I can tell you right now, because in this regime, in particular, if S is very, very large, but much lower than the Planck mass, then all the diagrams contributing to this process are this very simple diagram in which there is a particle exchange in a tree level, exponentiated. You take this diagram, you put this in an exponent, and if you develop the exponential, you get all the diagrams contributed to this process. So it's a very simple one. So the price to pay is that they depend only on if there is a graviton running in the internal leg, this 3-point graviton vertex, and it only depends on the 3-point graviton vertex. So if I want to put the quartic Riemann term, no, remember that here I put only up to cubic. I didn't put the quartic, which is in the dots here, because the quartic term doesn't contribute to the 3-point vertex. You take the quartic term, you take ADS or flat space, you perturb it, you then analyze the vertices of the perturbations, and you can see that the quartic terms do not contribute to the 3-point vertex. So the only two contributions come from the quadratic and the cubic terms. One more thing, I said I didn't put here the Gauss-Bonnet combination, but I put the Riemann square. Why? Well, because it's enough. Because the language of scattering amplitudes is independent of field redefinitions. And any term involving the Ricci and the scalar of curvature can be obtained by field redefinitions of the metric. So then I can neglect them. I cannot consider them because I can create them back if I need them. So whenever I put the Riemann square, I am also implying Gauss-Bonnet here. Whenever I put the Riemann cube, I am also implying Lovelock cube. And this will be very important for a reason that will be clear in a second. So, of course, in particle physics, there are books about how to compute this. And it's very nice that in the particular case of fixed impact parameter, the scattering matrix depends on a single thing, which is called the iconal phase shift. And it's the integral, is like sort of the Fourier transform of this amplitude. Okay, so this amplitude contains the left vertex, the propagator, and the right vertex. Left, right, propagator. So now what I can do is to see how the quadratic and cubic term affect those vertices. Of course, it's a very long computation. I'm not going to show you, but conceptually simple. I mean, you have to simply see how these quadratic and cubic terms affect the vertices. So this is the 3-point vertex in which you have the Einstein-Hilbert contribution. E is the polarization of the graviton. This is a canonical for those who ever checked the graviton scattering in GR. This is the term in GR. This is a contribution coming from the Gauss-Bonnet term, quadratic, and this is a contribution coming from the cubic term. Of course, the same for the right vertex. Then I have to multiply these two. No, I have to multiply these two. So then the multiplication has pu squared, pb squared. But maybe you remember that pu, pb is s. So this is an s square factor in the numerator. But in the definition, there is an s factor in the denominator. So then the S matrix, well, the phase shift goes like S in the large S limit. This means that the S matrix, that as I told you is the exponential of that quantity, will be in the large S limit, will be e to the is. But one of the conditions that you have to have an analytic S matrix is that in the complex S, well, there are two S's here. The green S is the S matrix. The blue S is the blue and lower S is the Mandelstam variable. In the complex Mandelstam S variable plane, in the upper half, this quantity has to have a modulus lower or equal 1. So then, if imagine that I write here the real and the imaginary part. The imaginary part, I times I is minus 1. So it will give me a E minus the imaginary part of S. And this is, if the imaginary part of S is positive, this will be below 1, which is okay. But if I am allowed to flip the sign of delta, that will take things inside the circle modulus equals 1 to outside the circle. So I cannot allow for sign flips in delta. Okay? A sign flip in delta will make a theory non-analytic, and the S matrix will be not bounded in the circle of modulus 1 in the Mandelstam plane. Now, we showed in our paper that you cannot do that. You cannot do that. Why? Well, so you can you can see how this delta is computed in the gravity side. Um, well, delta in the gravity side, sorry. So delta is already in the gravity side, is the phase shift of the gravitons. But what you can do is a different computation in which you can use one of the gravitons as a sort of source, and the other graviton moving in the background of the graviton creating a space-time background. The space-time background is a shock wave, so the problem reduces to a graviton moving in a shock wave. And then maybe you have seen in the course of gravitation in the career that there is something called Shapiro delay when a particle, any particle, in particular light or a graviton, passes nearby a massive thing, it will um, reduce a little bit the speed, so there will be a delay in its propagation as compared to the time it would take if there was no massive source. This was proposed by Shapiro in the 60s, and it was immediately checked to be truth using the Vikings satellites around Mars. They use the signal and also around satellites, artificial satellites in Venus. What they use is a radar signals that echoed in these satellites, and people found out that whenever Mars was almost entering behind the sun, there was a further delay to the signal, exactly a Shapiro delay. So this is something you can compute in GR. It's in the book, in Weinberg's book. You can find it. It's an exercise. You can compute it and you can do the experiment. You can find this is true. Now, delta is proportional to the Shapiro delay. If you want, is equal to the Shapiro delay. There is a proportionality factor, but it never minds. That means that a flip of sign in delta would mean a flip of sign in Shapiro delay. So it would mean a delay converted into an advance. It will mean that the particle comes through the massive body and it goes faster than light instead of slower than light. Still, it's not obvious that this violates causality because, for instance, if you take a signal to Mars back and forth, the delay will be 200 microseconds. So, and of course, the light will take like 30 minutes to go there. So it's not, the amount of the Shapiro delay or Shapiro advance is so small compared to the total time of the signal that if it's an advance, it will not violate causality in an obvious way. But theoretically, you can do and we did in the paper with great detail, you can do a series of shock waves, so you can show that you can make the Shapiro advance finite, so to say, above the uncertainty principle. So we checked all the subtleties you can imagine. So we checked that there is an advance whenever delta flips signs. And the point is that, again, you analyze the graviton with the tensor mode of the graviton, the vector mode of the graviton, the scalar mode of the graviton. This means, why do you have a tensor, vector, and scalar? Because you have the polarization of the graviton and you have the impact parameter. So you have a vector and a tensor. With that, you can define the vector, tensor, and scalar channels. And you can show that the tensor channel and the scalar channel always have opposite signs. So one of them will violate Shapiro or will violate analyticity of this matrix. And if you flip the signs of C1 and C2, the coefficients in the Lagrangian, the only thing you will make is interchange the roles. So if the tensor was the one violating Shapiro and you flip the sign, now it will be the scalar mode. But always there will be someone violating the causality. Now, remember that we are thinking that the higher curvature terms are coming from an effective field theory approach. In that case, whenever you have something like this, causality violation, the typical thing you try is, okay, in the effective field theory, supposedly, I integrated out all degrees of freedom, and I'm focusing on the only remaining degrees of freedom at a given energy. I integrate everything with energies above this energy I choose. So maybe I am finding this problem because I mistakenly integrated out some degree of freedom that has energy that is the order of or below the cutoff I use for the effective field theory. This is very canonical in QFTs. So this is the first thing you may think. So imagine that there were some degrees of freedom we integrated out by mistake. Then it's very easy to show that if that degree of freedom has spin j, the contribution of that degree of freedom running here, no, that means I am thinking of a degree of freedom running in this line. So the contribution of that degree of freedom will be s to the j minus 1. This you can show. So this is one striking thing, is that neither scalars nor vectors nor gravitinos will help you, because all of them will lead you to j minus 1 below 1, and the problem arises at order 1. Of course, the first thing you may think, and this is what we thought, is j equals 2, because j equals 2 will be massive gravitons, for instance, massive modes for the graviton that maybe with the right sign will cancel this problem and this problem will disappear. But you can, and this will be very interesting because massive gravitons would be the sign of higher dimensions. So you may be finding signs of the existence of higher dimensions out of consistency of the effective field theory approach to GR. But unfortunately, if you take a massive spin 2 field, in a massive, I will go very fast through the argument, in a massive, if the internal particle is massive, you can go to the rest frame of the massive particle, and then you can show that the helicity of the incoming graviton, the outcoming graviton, they cannot flip the helicity. So then the massive graviton would have to be spin 4 for angular momentum conservation, and this doesn't work. That means j equals 2 and a massive particle work from the point of view of the behavior of delta, but they do not conserve angular momentum. Those plots in the iconal limit cannot contribute to the scattering amplitude. So the only possibility we found is to have j greater than 2, but then of course you will kill the problem of gravitons and you will create a problem on your own. Imagine you put j equals 3. 3 minus 1 tends to be 2. So you will have a particle removing the large S behavior of the graviton, but it will create a problem on itself. So then you would say, okay, let me put a spin 4 to solve the problem of the spin 3, and then a spin 5 to solve the problem of spin 4. Well, anyway, we need an infinite tower of higher spin particles. And on top of that, they must have the coupling of those particles in the Lagrangian or in the theory have to be delicately tuned such that the sum of all the powers of S adds up to a non-analytic function in delta. Because if not, you will always have the problem. It's an iterative process in which every particle solves the problem of the previous, but creates a problem on its own. So we found this result, and then shortly after our paper, there was this beautiful paper by Veneziano and collaborators. Veneziano is, as you know, is the father of string theory, and is an expert on this kind of scattering amplitudes. And they showed a beautiful result in which they showed that the high energy interaction of a string and a brane didn't have this problem. But if artificially you remove one particle from the string spectrum, you create the problem. So all in all, apparently what we are finding is that you need the whole tower of the string spectrum to solve this problem. In other words, to summarize, and wake up if you fell asleep, if you have quadratic and cubic couplings, my message would be, you are violating causality, which is not something acceptable, unless they are part of either string theory or a theory that has that particular feature of string theory, an infinite tower of higher spin particles with a tuned coupling. So this is in a sense, an attempt to show that string theory is the only theory making sense of these higher curvature terms. Of course, it's not a theorem. It's not Lovelock's theorem. This is not a theorem. So it has a lot of caveats and things that can be argued. And there were many papers confronting our result and who do not agree with our result. Still, I think the result is correct. Proviso, of course, some assumptions that I'll try to explain. So notice that this is also the case for Gauss-Bonnet. So Gauss-Bonnet, that I started my lecture saying Gauss-Bonnet is a beautiful theory, second order equations, everything works well. Well, no, I lied. There is a, well, I then showed that there was a finite window in which it didn't violate causality. Well, no, the window is very tiny. It's very nearby zero and it's only Planck order. You can depart from zero a Planck order value, except if you remember that there is some further stuff in the theory, this higher spin tower of particles. Okay, since in this case causality was in conflict with in a theory like Gauss-Bonnet, in which all apparently was a theory without any problem. Then we went to the three-dimensional case because I will jump this because I think it's more interesting. Three-dimensional case is very particular because it's a case, any of you who worked on this, there is something very weird. In 3D, gravity doesn't propagate, but if you introduce some corrections like this one here, then there are gravitons. And then sigma is the Newton constant, and there is something very weird. In order for the gravitons to propagate with the right kinetic term, you need the Newton constant to be negative. But in order to have black holes, you need the Newton constant to be positive. So we asked ourselves, whether causality chooses one of the signs. And causality chooses the sign of the negative value of sigma. So it chooses the same sign than the right well-behaved graviton propagator. So we did this for many, many three-dimensional theories. I am jumping also. Well, then we also analyzed, remember I told you there were more branches than the branch, there are many branches in these theories. So in this paper, we analyzed what happens in the other branch, and then recently I analyzed the combination of two problems. Well, I'm jumping. You can find this in the, I will then send the PDF, okay, of the talk. Let me very briefly, well, this was a very striking result. We found that if we take the Gauss-Bonnet theory that violated causality, and you add up the quadratic Ricci and quadratic scalar, supposedly they shouldn't do anything because they can be removed by field redefinition, unless you are in a solution that is non-perturbative compared to GR. Then the field definition might be ill-defined. So this is the case we analyzed in this last paper. I showed the reference in the previous slide, and we showed that the ghosts can help to restore causality. This is something very strange, but it's in line with many papers appearing in the last 2 or 3 years, showing that the ghosts, that as Hawking would have said, and actually he said in a paper, we shouldn't be afraid of ghosts or maybe we shouldn't be as afraid of ghosts as first we may think. Let me take the last minute in showing. Let's even regardless of all the problems I told you, and never mind, I will try to analyze what happens when you put in 4 dimensions these higher curvature corrections, in which I can imagine that I turned off, all the higher spin fields, and I will analyze only the gravity part. So this, the Einstein Hill production, the cosmological term, and this written here is an infinite series of all higher curvature terms, in which R curly R is a particular combination of those terms. So I will go to that particular combination to I cannot demand second order equations, because if not, the Lovelock theorem will tell me that I cannot add anything in 4 dimensions. But I will ask softer things at the Lovelock theorem, and I will see where it takes me. So I will choose these coefficients. It's an infinite set of coefficients. Of course, this is problematic to have a theory with infinite parameters, but okay, I will try to use that in my favor so I can choose whatever I want here. Supposedly, if this comes from a given UV completed theory, like string theory will tell you how to compute these lambdas, at least in principle. The computation can be a nightmare, but there is a recipe to compute them. So in string theory, these lambdas come from a computation. I will play bottom up. So I will write the theory without knowing where it comes from. So I will choose the lambdas in such a way that, remember that when I had a theory of order k, I had k vacua. If I have a theory of order infinity, I may have an infinity of vacua. I don't want that at the moment, so I will choose lambdas in such a way that there is only one vacuum. But I can always do, because remember there were excluded vacua, no, that I can just like lambda greater than 1/4 I showed at the beginning. So I will do whatever I need to have only one vacuum. The vacuum will be the one connected to GR. So if I take all the couplings to 0, that limit will take me to GR. And then in general, you can show that you write the equations of motion of these theories. And in general, no matter what you write here, as soon as you don't use covariant derivatives, you just use Riemanns and contractions with the metric, you will find that there are 3 degrees of freedom. The graviton, good. A ghosty massive graviton, that means a massive graviton with the wrong sign in the kinetic term, bad. And the scalar field, okay, no problem. I will kill the ghostly massive graviton and the scalar field. The killing of the scalar field is not necessary, but I will do it just to analyze a simpler and simpler family of theories. So my imposition will be, I want to have massless gravitons, and on top of that, I want them to have Einstein's dynamics, which is what we expect. I want to have well-behaved black hole solutions, so no black holes that have dramatic instabilities, negative temperatures, or, so I will be very conservative, black holes that are, actually my definition of well-behaved black holes will be black holes whose ansatz is minus f dt squared plus dr squared over f. You can have black holes in which f, and these are two different functions, but I will choose to impose that they are the same function. And finally, I will ask a well-posed initial value problem for cosmology, and I will be more specific in a second about that. If I impose the first 2 conditions at quadratic level, there is a unique solution. You can prove that. And the unique solution, this was proved by Pablo Bueno and Pablo Cano. The reference is here, sorry, is this one here. And the only combination is the Gauss-Bonnet combination. Okay, so this is bad news in a sense, because this means that in 4 dimensions, this term is a total derivative. This means that there is no quadratic correction to Einstein-Hilbert action in 4 dimensions, satisfying the first 2 conditions. Not to talk about the fourth, only with the first 2. Now, if you ask at the cubic level, there are 2 possibilities. The Pablo Bueno and Pablo Cano, who were the first to do this, they show that this combination of cubic terms satisfies the first 2 conditions. Then Hennigar, Kubitschek, and Mann showed that there was another combination that satisfies these 2 conditions, but this combination is somehow trivial in a sense, because if you plug the ansatz for the black hole solution in the equations of motion coming from Lagrangian Z, what you have is 0 equals 0. You have no equation, actually. They just vanish in the ansatz of not only of the black holes, but also in a more general ground of Einstein spaces. Now, something that was very exciting when we found it is that there is a single combination of these 2 guys, which is P minus 8c, that satisfies the third condition. So then there is the cubic answer to these 3 conditions is unique. And as you know, for a theoretician, uniqueness makes you scream Eureka and running in the streets naked, as Archimedes. So if you analyze, furthermore, if you analyze the cosmology arising in that particular case, the result is an accelerating cosmology. So you don't need an inflaton to accelerate the expansion of the universe with this particular cubic term that I am putting here. Then, very soon after, it was showed I saw that Julio is connected, Julio Oliva and collaborators. They showed that this is also true in the quartic case, and people generalize this very quickly. And actually, we ourselves, with the Pablo Bueno, Pablo Cano, Robbie Hennigar, and also Gustavo Arciniega and Luisa Jaime, who were my collaborators in the first paper, In a month, we found out how to do this for any order. So for any order in 4 dimensions, we take the ansatz to the Friedmann-Lemaitre-Robertson-Walker space-time as we do in cosmology. We change variables from the time to the e-false to analyze the expansion of the universe. We plug everything into the Friedmann equations, and we get something very similar to the black holes before. We get that the Friedmann equation becomes an algebraic equation. So this function, which is a series, an even series in the Hubble constant, with the coefficients, of course, fixed by the coefficients of the action, equal to the density of whatever you have, radiation, matter, the inflaton, whatever you want to put there, whatever matter content you put to the universe. But this is what I meant by a well-behaved initial value problem. If this Friedmann equation doesn't involve derivatives of the Hubble constant, this means that this is second order in the scale factor a of as a function of time obeys a second order equation of motion, which is what we were looking for here. This equation you can always forget because with the continuity equation or the conservation equations and this one you can prove that this equation also holds. So then we found a cosmology, and I am going to finish in a couple of minutes. You find a cosmology that is, in a sense, as simple as the black holes we discussed before. It's simply equating an algebraic equation with a density here. So, okay, there are lots of things I cannot discuss, but let me just show you a plot. ADS applications, there are many things. Unfortunately, it was well, probably the content was too much for 2 hours. So this is, for instance, the lambda CDM at the lambda CDM at the early universe. You find that A goes to 0. This is a black hole the Big Bang singularity that I don't know, Lemaitre realized a century ago, and then Hawking and Penrose proved that this was true regardless of the symmetries. But then, and of course, we don't believe in this point, but okay, this is the behavior of the land of CDM cosmology. The so-called geometric inflation, this is the fancy name we gave to the theory, gives you an exponential or something behaving like an exponential. So clearly, because of the concavity of the curve, there is an accelerated expansion period that then softly joins the GR prediction. So it was very beautiful because it was something created by the higher curvature terms, but then as soon as the curvature go low enough, it was going smoothly to the GR prediction. Actually, of course, you have all the freedom that the lambdas, you have an infinite number of parameters, but we play with some cases, and the generic answer was that you get very easily, as you can see here, you can get very easily 60, 80 e-folds, and which are sufficient to solve one of the problems, to solve the flatness problem, and the horizon problem of inflation. There are, of course, other problems of inflation that are much more complicated, which is analyzing the perturbations of the analysis of the perturbations leading to the CMB. This we didn't do. This is very hard. We didn't do. Actually, we tried, and we don't know if it can be done, actually. I'm going to finish here. Let me just flash the slides to show you very briefly, to mention some things, just in case someone has been following me up to this point. After we wrote that paper, there were people complaining our result, contesting our result, including Starobinsky, who is one of the fathers of inflation. Okay. I mean, okay, the arguments are reasonable, but we still think that they are not, they can be also, we have counter arguments to them. In particular, we realized in this paper that there is a problem that I will briefly flash, which is that in order to have inflation, even if naively it seems that you need inflation, if you analyze carefully, you need Transplanckian densities. So you need rho, the initial density that triggers inflation, has to be, in order to produce the number of e-folds you wanted, has to be above the Planck mass to the fourth power. So then we went to the basket, the waste basket in which the inflaton was lying there because we thought we could kill the inflaton. We asked for his forgiveness, and we brought back the inflaton. And the scenario when you brought back the inflaton is beautiful because what happens, let me show you in a plot. This is a beautiful plot that I think you will be able to understand. This is the red figure is the inflaton. The and this is the epsilon parameter of the slow roll epsilon parameter. If it's below 1, the universe is inflating. And then you can see that here we analyze the quartic theory. The prediction of the quartic theory is that the epsilon should be 1/2. And as you see at the beginning, the quartic term governs the expansion, and epsilon is 1/2. Sorry, you have epsilon in the right-hand side. Epsilon is 1/2. Then at some point, it jumps to 2/3, which is the value of the cubic term. And then suddenly it drops to 0 and it grows like in GR. So it means that the terms govern the expansion of the universe in consecutive, so the first the quartic, then the cubic, then GR. And the unexpected thing is that the inflaton field remains almost constant during these quadratic, cubic, and quartic periods. That allows us to take the inflaton field well below the GR value that has a problem. I don't know if you know, but in GR, you need a transplanckian inflaton to produce inflation. In this way, we show that the combination of geometric inflation and the inflaton can solve this transplanckian issue. Actually, this is a quartic example, but then just to show you a plot, this is the infinite number of terms. When you add an infinite number of terms, then you have that, for instance, the inflaton field can be 0.01 in the Planck units. This is impossible in GR. And then still you can have ADE faults very easily. So generically, you can solve this transplanckian problem, and this is something I think deserves further attention, although, well, some deserve further attention. So give me 2 minutes just to show you another thing that it has to be published very soon, hopefully, which is what these terms would imply for accretion of black holes. And let me show you just this. So the idea, we found some hints in very simple systems that higher curvature terms favor accretion of matter from black holes in two different ways. First, if you put cubic or quartic or whatever terms, the black hole grows. So of course, if it grows, it has a larger cross section. But also the geodesics are more focused. So then there is like a double effect that improves the capability to accrete matter of the black holes. So we found in generically, and I'm showing you some random plots, but we did the analysis of what is called wind accretion, a black hole going through a medium, and also a black hole in a fluid. In all the cases we analyzed it, we found out that the m dot, which is the increase of the mass because of accretion, if you take this, this is the black curve is a GR prediction. These are a consecutive, you turn on and increase the cubic term in the theory that Pablo Bueno and Pablo Cano obtained a few years ago, and you see that the accretion goes up. And it goes up in a way that in principle might lead to observable features. I have no time to tell you, but okay, if you analyze particular systems, and we joined effort with Tejeda, who is a Mexican astrophysicist, because we are theoretical physicists, so we need someone knowing about what the kind of systems out in space that can lead to observations that we may eventually say something about them, and in particular there are systems that are in which we can apply this. So let me just go to the conclusions. I will flash. There are many open questions, many. So there is a lot of things to be done. So I hope, and I am finishing, that this flash introduction to higher curvature corrections, that again, let me re-express that this is something very personal, because there are people working in this subject that will fully disagree in probably whatever I decided to point out. There are other ADS-CFT applications. There are other astrophysical applications of these theories that are very interesting. There are many papers on this subject, but I wanted to give a sort of, well, a very, I think, quite complete theoretical approach to them. So now you know the limitations and the caveats, and about the applications, I went very fast over them. So thank you for your attention, and sorry for being a bit late.